Good evening, viewers. Now we'll start today's lecture 2, and we'll study vector space. So first we'll see its definition. So what is the definition of vector space? A non-empty set V, is said to be a vector space. Over a field F if it satisfies the following properties. Under the operation addition and scalar multiplication. Okay. So what are the properties of this addition and scalar multiplication? First I will write some properties of addition. Previously I already told you what is the definition of field and what are the properties of field, and also I told there it has to satisfy 5 properties of addition, all properties of addition, and similarly here also a vector space V is said to be a vector space, a non-empty set V is said to be a vector space over a field F if it satisfies all properties of addition, and also there are some properties of scalar multiplication. Okay, now I will write all the properties of addition, like closure property of addition. So what is the closure property of addition? It says that U plus V belongs to V. For all U comma V belongs to V. So you have to say this V as a vector space if you will take any two elements, or you can say any two vectors U and V, or any two element U and V, small u and small v, from that non-empty set V, then their sum is also lie in V. Okay, that is the closure property of addition. Similarly, commutative property of addition, that is U plus V is equal to V plus U. For all U V belongs to set V, small u and small v belongs to set V, then small u plus small v equal to small v plus small u. That means they are commutative with respect to addition. Then next property, associative property of addition. And it says U plus V plus W, V plus W is in bracket, is equal to U plus V in bracket plus W, where U, V, W belongs to that non-empty set V. Okay. Then next property, existence of additive identity element. Existence of additive identity element in V. And we know the additive identity element is 0. That means 0 must exist in V. So we can say for all U belongs to V, there exists 0 belongs to V such that U plus 0 equal to 0 plus U equal to U. For all U belongs to V, that 0 must present in the set V. Okay, that is the existence of additive identity element in V. Then next, existence of additive inverse element. Existence of additive inverse element, additive inverse element in V. That is, for all U belongs to V, there exists minus U belongs to V such that U plus minus U equal to minus U plus U equal to 0. So these are all the properties of operation addition. Similarly, it has to satisfy some properties of scalar multiplication also. So we can write some properties of scalar multiplication. Some properties of scalar multiplication. Then its first property is closure property of scalar multiplication. Closure property of scalar multiplication. So what do we mean by closure property of scalar multiplication? So the closure property of scalar multiplication says if alpha belongs to scalar f, what is the f? I already told you a non-empty set B is said to be a vector space over a field F. So that alpha must belongs to that field F. Okay. So if alpha belongs to F and U belongs to that non-empty set B, then alpha into U must belongs to V. If alpha is any scalar, that means alpha belongs to set F or belongs to that field F where the V is said to be a vector space, and small u belongs to that non-empty set V, then their product must lie on that set V. Okay, that is the closure property of scalar multiplication. That means when you take an element u from set V, and if you will multiply a scalar from that field F, then the product must lie on, or if the product is lying in set V, then you will say that the V by non-empty set V is satisfying the closure property of scalar multiplication. Then the next property is distributive property. So what is distributive property? So distributive property, there are two types. Suppose alpha times u plus v is in bracket. Alpha times u plus v can be written as alpha into u plus alpha into v, where alpha is scalar, that means alpha belongs to f, and u comma v, small u comma small v belongs to that non-empty set v. And second, alpha plus beta into u equal to alpha into u plus beta into u, where alpha comma beta belongs to field F, that means alpha beta are scalars, and small u belongs to V. So here we can say the first property as your scalar multiplication is distributive over vector addition. Scalar multiplication is distributive. This is distributive over vector addition. And the second one, we can say the Vector multiplication is distributive over scalar addition. Vector multiplication is distributive over scalar addition. Okay. Then comes to a third property. After closure property of scalar multiplication and then distributive property, then associative property. So what is your associative property? Or associative property of scalar multiplication, you can say that is alpha beta times u must be equal to alpha times beta u, and this thing is also equal to beta times alpha u, where alpha beta are two scalars and u belongs to v. And the last property, that is 1 into u equal to u for all u belongs to set non-empty set v. That means if you take any element from v, that is u, then u into 1 must be equal to u. Okay. So if any non-empty set v satisfies all these 5 plus 4, all these 9 properties over a field f, then we will say V is a vector space over field f. Okay, so a non-empty set V is said to be a field over f if it satisfies all the above 9 properties. And you remember here, I am following this book, An Introduction to Linear Algebra. Okay, I am following this book, An Introduction to Linear Algebra, and its author is V. Krishnamurthy, along with other 2 authors are also there, and I am saying only the first author, that is V. Krishnamurthy. And I will follow this book for whole my unit 1 and half of unit 2, and then I will follow another book of linear algebra, by Friedberg, Friedberg. That is the rest part of unit 2 and all the unit 3 and unit 4. Okay, so basically I will follow all only these 2 books. So since I am for this unit 1, since I am following this Introduction to Linear Algebra by V. Krishnamurthy book, and this book is silent about this field. That means if any question is asking about any non-empty set V is a field, sorry, V is a vector space. So if question is asking to show that any non-empty set V is a vector space, that means this is asking V is a vector space over a field F, which is a set of real number. Okay, so anything is showing to show that, if anything is asking so that this is a vector space, that means you have to assume that it is asking you to show that V is a vector space over the field R, set of real number. Okay, that means by default you have to assume it. By default you have to assume R is the field. And also here it is saying for V2 which is your R2, that is your R cross R. Similarly, it is notation for V3, that is your R3, that means your R cross R. This is your plane 2D and this is your space 3D like this, and Vn represents Rn. Okay, these are the some different notations of this V Krishnamurti book. So while I will do some problem, I will remind you these things. Other books are not saying this thing. Okay, so now we know all the properties of vector space. Now I will try to solve a problem. Okay, so first I want to show that V2 is a vector space. So that V2, which is equivalent to your R2, is a vector space. Okay, so this is a vector space, and here the field is silent, that means you have to assume over field R. Over field R, that means your field is your set of real number R. So how we will show this? Now come to its solution, and we know a non-empty set V or a non-empty set is said to be a vector space if it satisfies 9 properties, and 5 properties from addition and rest 4 properties from scalar multiplication. Now comes to the first property, that is closure property of addition. What is the closure property of addition? Okay, so the property says you have to take 2 elements from this set. So we can take, let u comma v belongs to your v2. V2 means your R2. So if you will take 2 element u comma v from v2, so how it looks like, you know, v2 means this is R2 and this is R2 means this is 2D. 2D means this is R cross R. So this is a order pair. If you will take any element from R2, that must looks like an order pair. So how now I can define this u and v as, or I can say defining u is equal to u1 comma u2. Since these are 2D or order pair, so u equal to u1 u2 and v is equal to v1 comma v2. Now what is my aim? If you will take any 2 element uv belongs to that non-empty set, then their sum must lie on that set. So if I will consider my u plus v, this will be your u1 comma u2 plus v1 comma v2, and if we will add these 2 order pair, we know the addition rule in 2D or in order pair system. That means you have to add first element with the first element, that means u1 with the first coordinate with first coordinate and second coordinate with second coordinate. So I can write this one as, this is u1 plus v1 comma u2 plus v2. Okay, so here u plus v equal to u1 plus v1 comma u2 plus v2, and you can say since v2 is your r2, so what you will write in 2 coordinate system, this u1 u2 or v1 v2, so this must belongs to r, this must belongs to r, and this must belongs to r, and this must belongs to r. So here I can write where this u1 u2 v1 v2 belongs to r. So if we will see this u1 plus u2, this must belongs to R and this must belongs to R. So this is an element of R, this is another element of R. So this order pair must belongs to R2, that means this must belongs to V2. Okay, so this property is satisfied. Means if you take any two element U and V from V2, then their sum is also lying in V2 because its sum is also an order pair. Okay, so I can write thus closure property of addition is satisfying. Thus closure property of addition is satisfying. So in second I can write commutative property of addition. Commutative property of addition. So what is commutative property of addition? Similarly, my definition of u1v is same. I will take two elements, that is uv belongs to v2. Now I will show u plus v equal to v plus u. So now I will start from what is u plus v, and my definition of u1v this one. So u plus v means this is u1 comma u2, that is your u, and v1 comma v2, that is your v. So its addition means this is coordinate wise addition, first coordinate with first coordinate, then second coordinate with second coordinate. So this is u1 plus v1, then u2 plus v2. Okay, so I can write this one as this is v1 plus u1 because u1 plus v1 is same as v1 plus u1. Then u2 plus v2 is same as v2 plus u2, and I can write this one as this is v1 comma v2 plus u1 comma u2, which is your v plus u. So u plus v is your v plus u, where u and v are arbitrary elements of v2. So this property is also satisfied. Then come to third property. After closure and commutative, then next property is associative. So this is associative property of addition. Associative property of addition. So similarly, I have to take three elements. Let u, v, w belongs to v2, and uv is defined previously, and here I will define only w, defining w equal to w1 comma w2. Okay, so now if I will calculate this u plus v plus w, because you see the property here, the property says u plus v plus w equal to u plus v plus w. So first I will calculate what is this one, then next I will calculate what is the left hand side. I will simplify, then I will simplify the right hand side, then I will show both are equal. Okay, so if I will start from left hand side, or I can write this one as my left hand side. This is u plus v plus w. So u means this is u1 comma u2, then v means this is v1 comma v2, then w means this is w1 comma w2. Then if you will add, this is u1 comma u2 remains same. First you have to do the bracket work. So bracket work, what is this one? This is v1 plus w1 comma v2 plus w2. Okay, now this is belongs to v2, this is another element from v2. So if you will add, I will get this is u1 plus v1 plus w1 comma u2 plus v2 plus w2. that is my LHS. Similarly, if I will come from RHS and your RHS says U plus V is in bracket then plus W. So if I will write this thing, what is your U? This is U1 comma U2 and your V is V1 comma V2. This is in bracket, then your W is W1 comma W2. So if I will do the bracket work first, then this will be U1 plus V1, then U2 plus V2, then plus W1 comma W2. Then if you will sum this thing coordinate wise, so you will get U1 plus V1 plus W1 equal to U2 plus V2 plus W2. Okay, so if you will see, this is same as this one, so LHS must be equal to RHS, so I can write U plus V plus W equal to U plus V plus W. Okay, so I can say the associative property of addition is satisfied. Then comes to the next property, existence of additive identity element in V. So what is the next property? That is property number 4, existence of additive identity element, existence of additive identity element in V2. And we know 0 element is the additive identity element. So 0 element in V2 means this is a 2D system, so 0 must be equal to an order pair, that is 0 comma 0. So 0 comma 0, this thing is an element from V2. So if you will take any element, let U be any element belongs to V2, then U plus 0, which must be equal to 0 plus U, which will be U. So that is we have to show. So if you will verify what is your U plus 0, that means this is your U1 comma U2 plus 0 comma 0, then this is your U1 comma U2, that is your U, that is U1 plus 0 equal to U. Similarly, what is your 0 plus U? 0 means 0 comma 0 and U means U1 comma U2, and if you will take their sum, this will be U1 comma U2, which is your U. So U plus 0 equal to 0 plus U equal to U. Similarly, next we will show the property number 5, that is existence of additive inverse. Existence of additive inverse element. Existence of additive inverse elements in V2. Okay. So additive inverse element, what is additive inverse element? So let U, which is U1 comma U2, belongs to V2. So I am taking any element U from V2. So if U is equal to this thing, then what will be minus U? So minus U must be minus U1 comma minus U2. Okay. So if I will add U plus minus U, and you just see if U1 U2 belongs to V2, then minus U1 minus U2 must belongs to V2, because if U1 belongs to R, then minus U1 belongs to R, and if U2 belongs to R, then minus U2 belongs to R. Okay, so if U belongs to this one, then minus U belongs to V2, then we will take their sum, that it must be your additive identity element. Okay, so now if I will take U plus minus U, that is U1 comma U2 plus minus u1 comma minus u2, that will be u1 minus u2, then sorry, u1 coordinate wise addition. So this is u1 plus minus u1, u1 plus minus u1, then u2 plus minus u2, which will be, this is 0 comma 0, that is 0. And similarly you can show minus u plus u is also 0. Similarly you can show. Okay, so this property is satisfying. Then comes to next property, that is your closure property of scalar multiplication. Okay, so that is your closure property of scalar multiplication. So what is closure property of scalar multiplication? And this property says you have to take any scalar that alpha belongs to scalar field is your f, scalar means from field, that alpha belongs to f and your f is the set of real number. Okay, so let alpha is any real number, and if you will say u belongs to your v2, and you know your u is v2 means this is u1 comma u2, I already defined before. Now if I will consider alpha into u, that must lie on v2, we have to show this thing. So if I will consider alpha into u, that is alpha into u1 comma u2, and when I will multiply a scalar on a 2D or an order pair, then that scalar is multiplied with each of its element. That means this can be written as this is alpha times u1 and alpha times u2. So since alpha is a real number, u1 is a real number, so product of two real number is another real number. Similarly, alpha is a real number and u2 is another real number, this product is another real number. So this is belongs to R, this is also belongs to R, so we can say this thing belongs to R2 or this thing belongs to V2. So closure property of scalar multiplication is satisfied. Then the next property, associative property for scalar multiplication. Associative, then I will show the distributive. Okay, first I am doing this associative property. So associative property of scalar multiplication. So what is associative property of scalar multiplication? So let alpha comma beta belongs to field f, it is a real number, and u which is your u1 comma u2 belongs to v2 be arbitrary. Okay, so now if I will consider alpha beta into u, so now we know what we have to show. We have to show this thing alpha beta, we have to show this thing alpha, to show that, that is roughly I am writing alpha beta into u equal to alpha times beta u, and this thing equal to beta times alpha u also. We have to show this thing. Okay, so now if I will consider alpha beta times u, so what is alpha beta times u? Alpha beta times u, this is alpha beta, u is u1 u2, that is your alpha beta u1 alpha beta u2. So this is your this thing. Similarly, if I will consider what is alpha times beta u, so this is alpha times beta times u1 u2, which is your alpha times beta u1 beta u2, which is your alpha beta u1 alpha beta u2. Similarly, beta times alpha u, that is your beta times alpha u1 alpha u2, which will be your beta alpha u1 beta alpha u2. And you know alpha into beta is same as beta into alpha, so this is alpha beta u1 alpha beta u2. So all these three things are equal, thus it satisfying the associative property of scalar multiplication. And similarly we can show that it satisfies distributive property. I am not writing this thing, you can show this thing. Okay, similarly we can show that it satisfies distributive property. So what is your distributive property? Alpha times u plus v equal to alpha u alpha v, where alpha is scalar and u comma v, that is your u comma v belongs to v2, and alpha plus beta into u equal to alpha into u plus beta into u, where alpha beta are scalars, that means belongs to field F, and u belongs to v2. Okay, this thing we have to show. Then what is the ninth property? You will show that. Okay, the ninth property is let u belongs to v2, that means u is your u1 comma u2, and if I will multiply 1 here, that is 1 into u, that will be your 1 into u1 comma u2, that will be your u1 comma u2, means 1 into u1 is u1, 1 into u2, that is your u2. You can write 1 into u1, 1 into u2, and which will be your u1 u2, that is your u. So 1 into u is your u, and here we show that all the 9 properties are satisfied. Okay, so you can say v2 is a vector space. Here v2 is a vector space. Okay, so now I want to show a problem, or I can say a theorem, which is very easy. And similarly like this, this is an exercise to show that Vn is a vector space. Vector space, that means there is vector space over R. Field is not mentioning, means you have to take that is R. So there is a theorem in any vector space V, so that alpha into 0 vector equal to 0 vector, where alpha is scalar. Okay, and 0 into u vector equal to 0 vector, where 0 is a scalar and u is a vector. And third we have to show minus 1 into u equal to minus u. So very shortly we have to do this thing. So okay, in the next class I will say this thing, because my net pack is going to finish. Okay, so today is only this much. Thank you.